So before we start, I'm going to review how LLMs work, and this is all before this new scaling paradigm and the chain of thought reasoning presentation. So just looking at it, and mostly when you interact with ChatGPT today or any LLM, it's just going to be a high-level overview. Again, a lot of nuance gets lost when you simplify things down, but I think it does a pretty good job of explaining it holistically. So the first thing that happens is we need something to train on. And so there's a lot of ways that you can get the data to actually train on. Different labs are going to do it differently. They may, Meta is going to use all your Instagram DMs to train on, and like different companies might just use an open source algorithm that scrapes the internet. But at the end of the day, what you want is you just want one continuous line of text, basically, that can be, up to 1 trillion tokens long and millions of words, but you just want one single line, which is all text data. And that's going to be the basis of your training and what you train on. There's, of course, multiple modalities that are trained on images and stuff as well, but just for simplification, we'll focus on just text. So after you get the text data, you have just, lines and lines of different words and sequences from articles and all this. And you just literally want a one-dimensional thing where you could just trace it down and read it essentially forever. And as people familiar with computer science, we probably all are, text is made up of words, which is made up of characters, which are represented as bits. And so you can actually take any single word and convert it to what the bits would actually be. And so the process of tokenization is just mostly done for efficiency. It would probably be better if we could train LLMs to read words and letters like we do, but it just makes sense to do this for efficiency's sake, basically. And so if you take a word like can't, right, there's a certain bit sequence that is going to correspond to. So if you look up here, I've kind of split it into what the actual bits would be. And so across that entire one-dimensional text stream, you're going to have a lot of sequence of bits that appear very frequently. And so for efficiency's sake, you can take those bits and kind of group them into what are called tokens. And so again, different labs and different programs are going to tokenize things slightly differently. But at the end of the day, you're basically just taking things that appear frequently and basically creating a mapping table so that you can access those things. And so when you feed the word can't into ChatGPT, what it will see is whatever OpenAI's tokenization algorithm decided was most efficient to represent it, which could be something like, oh, can is this sequence of some bits, which is token 357. That's just arbitrary. And the apostrophe T, that's going to appear a lot too. So that's token 7894. And so when you feed that in, it's seeing the two tokens separately. And that can actually lead to a lot of issues, which we'll get into later. But again, just looking at the entire text of the internet, converting it to bits, seeing what sequences of bits appear most commonly, turning those into tokens, and then moving forward with those tokens to do all the training. So the actual training happens in a neural network. I won't try to pretend I know exactly how this works, and even the inner workings of those are sort of complex and not always understood. But you want to take this, now you have a bunch of tokens, you still have, millions, billions of tokens that you want to process. So you're going to split those into chunks. Maybe you process 2,000 tokens at a time. And this happens at data centers that are huge. They could, take up entire blocks. This could be happening on, 100,000 GPUs over the course of 6 months, right? Because this is trillions of data points that you have to process. But the idea is you have your one-dimensional thing, and you're going to feed in one at a time and allow the model to guess the next word. And so if you fed in this example here, you would know because the text is already written out, you've already scraped it from somewhere, what words appear next, right? So you could feed in and the model might guess a word. And then like, oh, the word was actually cat. And then you feed in the cat and you see, oh, what word does it guess? And then you compare it to the actual word, which is sat. And so the guesses, they have to do with loss functions, which, I'm not too familiar with loss functions and how they work exactly in this context, but you want to be able to quantify how good of a guess the model made. And over time, you want to be able to sort of pass that back into the model and have it make better guesses over time. And so if we look at this specific example, the cat sat on the blank. The next actual word is couch. But the model, if it's still early in its training, it probably sees the word cat And it knows that's associated with dogs a lot because that comes up in the training data. When someone mentions cat, it mentions dogs. So it is kind of like a okay sounding sentence. It's like it makes like grammatical sense and like somewhat sense. Like a cat could sit on a dog, but it doesn't make much actual sense. And like the chance of that actually happening or appearing in the training data is gonna be low. And so the model guesses dog, it's actually couch. So then you're going to compare those, run the loss function, see the difference, and the model's going to have a way of updating it so the next time. And if you can imagine this happens millions of times, over time, the model is going to understand that a cat is probably likely to sit on these 5 objects, like a windowsill and a couch, and it's not very likely to sit on like a dog or a horse, even though animals are mentioned in groups. So over time, it can really get a web of like how the world works through this form of text. And yeah, again, the actual inner workings of the neural net is very complicated, but in general, you're going to be passing that word through, and at every sequence of these different functions, you're going to be getting more information about how to predict the next word and what to make a better guess. But the important part is that the training process happens by guessing the next word, and over time, the model gets super, super good at guessing the next word. And so when you're done with training, what you have is what's called a base model. So a base model is super, super good at predicting the next word, and it has a lot of knowledge about the world, but it is not what you interact with when you go on to ChatGPT or any, Gemini, anything. You can actually talk with a base model. There's sites online, they're open sourced a lot, so you could do that. But a base model is just the patterns that it's learned from the internet. And so if you ask a question, like, how do I solve this physics problem? It might be like, how do you solve this calculus problem? Like that might literally be its response because it's a grammatically correct sentence and it's a question that's related to the question you asked. But what you want is you want an answer. And so what happens at this phase is you have your base model and it's fine-tuned with reinforcement learning and human feedback. So what that means is you basically give the model probably a couple thousand examples of how to act, and you basically get the model to pretend like it's an assistant. And the model knows what an assistant is. It's been trained on the entire internet, so it has an idea of what an assistant is, but you have to give it examples of how that assistant should act. And so if you ever hear about like offshoring of like human labeling or like this AI company paid people overseas, like those were human labelers. Those people still have to be incredibly smart within their field because they have to be able to answer questions that the model looked up, but it also reveals areas that may not be the best for asking AI models that people tend to use it for. So something like if you ask like, what are the top 10 things to do in Paris? Likely that's a pretty common question. So OpenAI has probably paid someone overseas to read that question and write out exactly how the model should respond to it. So that person would take 30 minutes of their time. They would look up the 10 places in Paris. They would have a document that tells them exactly how they should respond to that. And, they're probably going to be super happy about it and be like, oh, yes, the top 10 places in Paris are this, 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 and then tells all about it. So if you went to ChatGPT and asked that, you would probably get the exact response that that labeler typed in. But over time, across thousands of examples, you start to get a persona for the model. And so the model can then know that like, oh, even though I've been trained on all these things to act as a user assistant, when someone asks me about a math question, I can use the 5 examples of how to answer a math question and extrapolate that and know how to act. But that's kind of the gist of it. And this is where humans are actually going to be most in the loop. It's where personality of models comes in. It's a super, super important part. And it's a part where if you sort of train wrong, you're only going on a basis of a few thousand examples. And so things can go wrong very, very quickly. So for example, if you were to train a model that when you ask complex problems, it had to answer with its first token, then that model is not going to be very smart because it only has one token to do this complex calculation. But if you have a model that first, yaps and yaps and yaps, and then it gives you the answer at the end, that model is going to be a little bit smarter because you're essentially giving the model more passes through the neural net to sort of process the information, and it can use all of those tokens to do the calculation. And so that's why sometimes you interact with these models and you're like, why do they talk so much? It can never just give me a straight answer. That's actually a feature because they, when you do that, you get more accurate answers, you reduce hallucinations. But over time, the model does learn and it sort of extrapolates and it gets this user assistant paradigm in it. So Before, if you asked the question to the base model before this step of training and said, how do I improve my morning routine? It might say something like, morning routines remind me of the eternal sunshine reflecting, right? So it's a sentence that makes sense. It's, somewhat cool sentence, and it's definitely related to the question that was asked, but it's not helpful. It's not what an assistant would say. If you ask someone that question, unless they were on drugs or something, they probably wouldn't give that response. Versus like the assistant, it's very methodical, like to improve your morning routine, you should consider, and then it's going to go into that. And it knows how to act as an assistant. It's probably seen, 1,000 articles on morning routines. So it's going to pull those facts from its neural net and respond. But obviously, this sort of approach it's kind of rudimentary. It's kind of throwing a bunch of data in. You get this like dream simulator that's really good at predicting the next word, and it can like speak a bunch of languages and understand nuance and grammar and style. But it's not really selecting for intelligence, I would say. And then you kind of just trick the model into thinking it's an assistant. Like that's what happens at the very end. So where it sort of acts like that assistant, that's like a last step. And so you aren't really breeding for any of those things that when we think of asking AI as like super magical thing that's going to like think about things and know everything. That's not really what we're interacting with when we talk to these LLMs. And so that's an important thing to understand. Okay, so this brings us to our first sort of interactive thing. So if you guys could just talk with the people around you or by yourself, just sort of think on this. Think about what are some potential problems. And if you go this URL, if you go on your computer, it's better. On the phone, I couldn't figure out how to like add it. But I'm just going to review them. It's not like required that you add them or anything. But if you guys, just talk to each other. And you've probably interacted with these LLMs a lot. So you know the problems that they have and why that they're related to this sort of paradigm. I'll start talking about some of these, but yeah, these are all related to the sort of predicament that current LLMs are in. So adjusting the response length to what the user needs, it's like it will be way too long, and then you're like, okay, make it a little bit shorter, slightly shorter, and then it'll like respond in 2 sentences. That's again just like it doesn't actually know how long its response is, and it can sort of make an educated guess that it needs to spend more time or less time, but it has no way to quantify that. And so as soon as and also when it sees the word shorter, that's just going to light up like, oh, I need to like do something shorter because it's only operating on a couple labeling examples from before. Why did chat start using emojis? So I know that they're trying to like make their model more like have a better personality. So why that happened is they probably updated their labeling examples to use more emojis because they thought that was a design decision that made it more personable or something. But yeah, because again, it's operating on so little ones. If you put emojis into like 10% of it, then certain things. And what I found too is like, if you talk about some topics, it won't use any emojis. Some it will just use like 100. So you've probably hit one of the examples that it has that person used a bunch of emojis when labeling. Again, like the response length one and hallucinations, because these models are meant to act sort of like egotistical and be like super happy and help you. They have a hard time just being like, I don't know. And like when you give someone a problem too, you would probably expect them to like break it down and like ask you follow-up questions. And that's just not a behavior we really see. These things have gotten better over time. And tool use is a really good one. So there's techniques you can use to basically get a model to understand when it doesn't know something and then look something up. And so there are ways, I think these are getting better, but there's also just a sort of fundamental limitation that we're acting in when we just do next word prediction and a user assistant. So these are some problems I listed. Yeah, hallucinations, do need to act confident. Inefficient log-based intelligence gains. So like you can scale it up and go from like 1 trillion tokens to 10 trillion tokens. And it's only going to give you a little bit more intelligence overall. And so that just doesn't seem efficient. If you knew a person that had consumed the entire internet and studied it, they would probably be the smartest person in the world by a long shot. And it doesn't feel like our current models today are those people. And there's definitely some problems there. And then lack of planning and instruction following, like I said, if I give you a super long task, you would probably ask some follow-up questions, break it down into parts, work it into your schedule. I don't think AI has to do that, but you would at least, kind of know, oh, I'm going to do this and I'm going to come back together. You would double check your work. And they just don't do that. They just kind of like, you give them the hardest problem ever, and they're just going to spend, a couple paragraphs trying to solve it, and just sort of lie if they didn't. And so there's a prediction for a long time that you could just sort of scale up. You could train on more data. You could give it more like examples in the labeling. You could, just scale up all of these different things. And we've seen that this has sort of worked because a lot of efficiency gains have happened. You have like really small models that can run on your phone that are, decently intelligent. ChatGPT is probably a lot smaller model every single time they push an update for economical reasons, which is again why it seems to be getting less smart because they're focused on efficiency. So the scaling paradigm is somewhat working, but I don't think a lot of the issues that we just talked about would be solved if we just scaled it up to 10 trillion tokens and trained on it, right? There's certain things that emerge when you do that, emergent properties, but I think there are fundamental limitations as well. So the question is, what if we scaled something else? What if we didn't focus on the training of these models, but instead focused on allowing them to plan and reason? And so what this is called is chain of thought reasoning. And so I'll just kind of start with an example to ground it and then work my way backwards. But I went to ChatGPT and asked the new model, what's the most important thing to mention in a presentation on chain of thought reasoning by LLMs? And so this is kind of its internal monologue, right? Again, I'm using the word thinking because I think it makes sense, but of course, I think we all know these aren't actual thinking beings. But I don't know, it sort of grounds it. So it says the user is asking what the most important thing to mention about chain of thought reasoning by LLM is. I think the key point is that chain of thought makes the reasoning process explicit, which improves transparency and helps reduce errors or hallucinations. It enhances interpretability and reliability as it breaks down complex problems into intermediate steps. So you can kind of see it's like telling itself what it should say. It's reminding itself what are some key points I should hit on. What should I do? What is the user asking me? And so it's kind of in this meta state of being where it's not just a user and assistant that has to like jump out and answer anymore. It's really slowing down and moving to like a level 2 style of thinking. And so that's just the general idea behind chain of thought reasoning. Let AI models think or plan or reason or whatever word you want to use before responding. And when you do that, you can kind of just ask ChatGPT a question, and for the most part, you're not really going to care what it thought about. But if you get a better response and you get something that's good, that allows it to actually think, but it doesn't have to like yap for all this time like it does right now, which can be pretty annoying. And it can generate a series of intermediate steps. So if there's complex planning, it could break a problem down. It could try out different steps and realize, okay, that's not that good. It could go back up, resume from a point. And all of this it could be doing, and you wouldn't have to like read through and make sure that you were finding the errors or you were double checking its work. It's more about it double checking its own work. And something that's important too to realize is that the best way for an LLM to reason is not the best way for a human to reason. And so it's kind of weird if you've played around with DeepSeek or heard about that. They expose the chain of thought directly. This was the big breakthrough of DeepSeek, is that they used this method. So they got really big intelligence gains out of a smaller model. But if you do read it, it's kind of interesting because it does seem like a person, and it's like thinking to itself. But these models, they're just very different than people, right? I mean, like they have jagged intelligence. They actually have been trained on like all of quantum physics and all of these complex topics, and they're very versatile. But then they have things that they're just really not good at. And so to try to like make it think the way we do wouldn't be very effective. An example of this I like to use is that sometimes, like 1 in 100 times, if you ask like ChatGPT or one of these reasoning models to think about a problem, it will randomly switch to another language in the middle of its thinking process and then switch back. And it's mostly in English because there's mostly English training data, but that's something that a human would probably never do. We would probably never switch to another language inside our head to think about a problem because there was more like information available in that language. But it does make sense for an LLM to do that, and you could see why that would be. So the question is, how do we actually train a model to think? And the key here is we don't train based on the process itself. We train on the result. And so this is kind of the idea of reinforcement learning and unsupervised learning, which is we don't go in and say, hey, you should think like this, this, and this, and you should break it down. We could try an approach like I was saying before with the labeling. Like you could hire the smartest physicists in the world and mathematicians, and you could pay them to break down these complex problems, and you could train the model to do that. But that would be really expensive. It's not sure if it would generalize, and you probably want to do millions upon millions of iterations of this, and that's not feasible to sort of pay people for that work and then also scale it up to that level. It just wouldn't really work. But you do want a data set of high quality reasoning problems. So you want very, very difficult problems. And you basically want to say like, okay, you have 1,000 attempts to think through this problem and solve it. And in the end, you can think for as long as you want in any way you want, but you have to give me one singular answer at the end. And so that gives you a very verifiable output. You can know like, oh, did it get this right? And so out of 1,000 ways it thinks, maybe 3 of them it got the right answer. And so then you reward those 3 ways of thinking. If you do this many, many times, eventually you're rewarding a good thinking and reasoning process that, again, it's not going to be the same way that people reason. And we're not even exactly sure the underlying techniques it's using. But the key is to let the model figure out on its own what the best reasoning steps are. So that was, again, another thing in the DeepSeek paper is that when they started out, they tried to do this very structured way and kind of clue the model in, hey, you should probably think like this. You should probably break stuff up. And when they sort of went the other route and just said, we're not going to tell the model anything, we're just going to let it decide what it thinks is best and reward the answer instead of the thinking, that's when they started to see those insane results and started to see the reasoning kind of scale. And so on that, something that in the DeepSeek paper they mentioned, and I'm mentioning DeepSeek a lot because their research paper is actually public, so you can read it, versus some of the other models, Gemini, OpenAI, they're not public, so they're kind of secretive about what they actually did. So very thankful that there's open scientific research there so we can get a peek into this process. But you can see this is how many steps, or basically how many steps, so how far along they were in the training process, in that iteration of like thousands upon thousands of training. Just steps, and then the length of response. And so over time, it learned that if it spends longer thinking about a problem, that it's going to do better. And so something that's implied in this is that it's getting more accurate as time goes on as well, because the loss function is actually working. But that seems to make sense. And that probably matches our intuition of what we would expect, that if we allowed models to think for a long, long time, that they could probably answer problems better because, maybe they can try something out. Maybe they can go back and double check their work. And just overall, longer thinking time is going to be better answers. And what this means is basically there's no longer as much of an emphasis in AI development on training itself, right? So the idea before was, okay, we could get GPT-5 and we could, train on 10 trillion tokens and run it for a year, and then we'll get all these rewards. But what this means is like, instead, reinforcement learning is relatively cheap and easy to do. We're letting the models think on its own. All we have to do is find, reasoning problems where there's a right answer and just know, is it right or is it wrong? And reward when it gets it right. But if we're saying that, okay, longer time reasoning, that means when you actually go and ask ChatGPT or any of these models a question, that there's going to be a lot more compute spent at the time of your question. And so if it thinks for, 20 minutes about something, then it's running that process over and over and over again, predicting the next word, even if it's inside its reasoning bubble, that's still a lot of compute. And so what this means is there'll be a shift in demand towards like inference compute rather than training compute. Because before, when we talked about in phase 1, basically after you train the base model, like it's done. You can't really fix it. You could redo the training run, you can do the labeling, but it's just a fixed set of parameters that aren't changing, where this is a little bit more fluid and could sort of scale. Like it could decide, I only need to think 1 second about this question, or I need to think 10 minutes about it. Okay, so now before we look at the results of this and how it actually turns out, I just wanted to do like a sort of like mini debate. I've kind of been cluing in that it does work and it is successful, or probably wouldn't be presenting on it. But if you're saying no, just you can always argue something you don't believe in, and just say like what things you still think it fails at or whatever. But yeah, I just think it's a good time to explore and just really think about it with someone. So yeah, does anyone want to try to like argue it? for their side. If not, that's okay, but we'll just move on. But Weston?
I mean, because you had mentioned like the no is like a little bit harder to argue. What we were kind of talking about reasons that you could say no to, and it's like how like when ChatGPT gets something wrong and you say, "Oh, you got it wrong," it immediately just agrees with you. Oh yeah, no, yeah, I definitely got it wrong. Like it's not really good at pushing back on the user, and it's probably not very good at pushing back on itself. So it can kind of get you in a situation where it comes up with a conclusion and then it just makes up reasons to justify the point.
Mm-hmm.
Because like again, you could give it a point and say justify this, and it could justify it. So if somewhere in intermediate logic it comes to the conclusion, everything beyond that's just kind of a preset notion. It's unlikely to correct itself. It's just it doesn't seem to correct
Yeah,
itself.
I think we were talking about like what's in the training data as well. So if there's like a gap in its training data, is it really self-aware enough to say like, oh, I don't know that, and be like, okay, so I should just kind of like do 80% of this problem and like let the user fill it in. Like, no, it's not trained to do that. It's gonna just like guess the last 20%, which is a hard balance too. So, all right, good point. So yeah, we'll look at the results. Benchmarks are just ways to test AI. I think we're going to be doing a presentation pretty relatively soon on benchmarks, but at the end of the day, it's like think about it like a midterm, right? You could maybe get like partial credit on some problems, but at the end of the day, you're probably right or you're wrong. And it's done through APIs, like you just kind of send the model through the API. So if there's not an API, it's pretty hard to benchmark stuff. So we look at the ARC AGI benchmark. This was a benchmark created in 2019 to show LLMs could not reason at all. Like they basically said that, yes, they're very smart, they're very good at some things, but they're just not generally reasonable. They're not anywhere close to AGI, which is a system thought to be generally reasonable and could learn a new task. And so humans score 85% on this. Seeing it for the first time, your average human, it doesn't matter. It's just a very simple visual task that you're going to score 85% on. Oh yeah, you hide there. But GPT-4o, which is the model that's mostly used in ChatGPT, scores only 5% on it. And like the original GPT series, GPT-2 scored like 2%. So we had all that gain in this other area. We had very, very little gain in this specific benchmark. And I don't remember the exact sort of challenge, but the creators set a prize and it was like 100,000 or $1 million if someone beat the human benchmark. And they estimated that based on current AI progress, it would be solved in 2028. And so just to give a little timeline here, OpenAI released O1 preview, and I think October, they announced it in like October, November of last year. They released full O1 in December, which was like their first series of this reasoning model, a model that was specifically trained with the chain of thought reasoning. And then last month they released, or sorry, at the beginning of this month, they didn't release the full one, they released a mini distilled version, but they announced O3, which confusingly is the second model. They just couldn't call it O2 for copyright reasons. But O3 is the second model in this. So they started training this, and only 3 months later, they have O3. And so O3 scored 87.5% on this general reasoning task. And so, of course, this is like a little bit of a skewed sort of graph because before we weren't trying to focus on reasoning, but now we are. But you can still see the progress of even when we are starting to focus on reasoning. O1 Preview was their first attempt on it. It only got 20%. And within 2 or 3 months, you have a model that's scoring 87.5% and got the $1 million prize. And so it does seem that, at least in a verifiable general reasoning task like this, that there is a sort of exponential gain. And like I said, this was kind of low-hanging fruit. It's something we would have expected the model to have been good at before, and it wasn't. But at least in the sense of filling in that gap, it did happen very, very rapidly when we used reinforcement learning. And if we look at something like a math benchmark, this is on the left here is the hardest high school math exam in the country. So if you do competition math, I don't know if anyone has ever done this test, but it's a very, very hard math problem. It's not to the college level, but very, very difficult. And on the left, we're seeing, again, O1 Preview. This was released 3 months ago, and it's starting at 56.7, where GPT-4o would get, I think somewhere around 10 to 20%. So already right away, when you just apply this rudimentary, you get amazing gains in math. And it scales very, very quickly because all they've done between O1 preview on the left here and O3 is they've just given more time to train the RL. They've just given harder problems and they've focused on rewarding the outputs. And so you can see very, very quickly, 96.7%. I believe that score was tied or better than any of the students that were competing in this. And then on the right here, this is problems, front research math. It was a benchmark that is at the cutting edge of math. So basically unsolved math problems that people could do, but just take very, very long time to do. So many PhD mathematicians have to come together to solve these math problems. And, they would get a very, very high score, 80, 90%. But the previous state of the art on this was only 2%, where O3 scored 25.2. And so this is pretty impressive and shows that, at least in some ways, it can do complex math. And so the difference in the bars there, like the shaded versus kind of unshaded one, is when they allowed it to think for a low amount of time versus allowed it to think for a high amount of time. So even in that, we can see, like, if we allow it to think for a long time, we're going to get better results. And then coding, on the left here, again, this is O1 preview to O3. So software engineering bench is a bench of real coding problems found in production of large companies. So this is not like leak code style problems or things that exist very much in the training data. This benchmark was created to show a more general and applicable benchmark for coding. So it's like after someone solves a production level problem that was taking them a long time, it can get added to the benchmark. And so you see very quickly that O1 preview did 40%. And again, other models probably get around 20 to 30% on this, but in just a couple months, there's a 30 percentage point gain, which is a very, very quick gain in something as important as coding. And then in competitive coding, O3 ranks the 175th best coder in the competitive code forces in the entire world. So the original 4.0 model was, I don't know, something like a millionth, and then just very, very quickly. And the reason you would see competitive coding, it would perform a lot better than production coding, is because competitive coding, there's a lot of training data on that, right? Leak code and all these Stack Overflow issues and kind of these courses that have been made to train people on your algorithmic style interview questions. That's abundant on the internet. So it has a lot of training data to use in its original base model and then at the end too, when they're doing the reinforcement learning step. And so if it's not obvious at this point, what works with this method is problems with verifiable outputs. So something like math, you either get the right answer or you get the wrong answer. And so it's very easy to let the model run 1,000 iterations and just reward the right answer. For something like coding, it's a little less right, wrong answer, but you could write 20 test cases and reward the model that writes something that passes the 20 test cases. So this is something that if it gets it right, you can reward it. If it gets it wrong, you don't reward it. And so things that require complex reasoning with a fixed amount of steps are going to see a pretty big improvement. But there are some things that it doesn't improve at basically at all with this technique. So domains that don't have straightforward reasoning. So if there's something where an answer may be more complex or have different solutions, it's probably going to perform better than it would have without the thinking process. But it's not going to be that sort of exponential gain that you're seeing here, just because it's harder to write a reward model that can give good answers there. And more creative elements with no right or wrong answer. So maybe if you asked a thinking model to write an essay, the high level structure or what it decided to write would flow better, but the actual writing would not probably be any better. It wouldn't be any more elegant, and it wouldn't be better than your average writer in college still, because that's something that's very, very hard to do. And you just can't, for reinforcement learning with human feedback, there's apparently just a fundamental limitation that if you train it enough times, the LLM will start to game the reinforcement learning algorithm for non-verifiable outputs. So if you want to have a model that's trained on how to write the best joke, well, eventually if you let it run for 20 hours and you check back in, you'll see that the best joke is because the model just found some loophole that was in there and exploited it. And so now you're not getting the best joke. You're just getting something that your reinforcement learning algorithm didn't really cover. That's reinforcement learning with human feedback, where there's, again, just not verifiable outputs. And so we are going to see a continuation. You're going to see more AI labs release these reasoning or thinking models, and they will excel at, math and coding and complex reasoning, but there are still unsolved issues in terms of creativity. And I would still say like a general intelligence, because I think someone who is that good at coding or math should be good at writing and stuff as well. Okay, and so yeah, just kind of one last discussion here. Just sort of identifying what problems still exist. I don't know if we talked about a lot of these earlier, but hallucination rates, for example, I think like GPT 4.0 on this hard benchmark had around like 10 to 12% hallucination rates. And the O3 model still had like 2 to 3%. So I mean, in hard fields where you want accuracy, 2 to 3 is still quite high. So it's still an issue. Slop, I feel like is kind of like the other end of like when I'm saying bad creative writing, or when it just, uses too many emojis or yaps too much. Energy costs, just those sorts of things. And so yeah, just kind of pick a problem that exists, talk about it. Why does it exist? Why do you think that's a result of training? And what could we scale up to fix this? And so we'll just talk for a couple of minutes, and then that'll be it for the meeting. But we'll do a couple of announcements after this as well.